Welcome back. This is lecture 15. So in the previous lecture we were discussing how to bias our common source amplifier, right? So we were discussing how to bias our common source amplifier, at least on the side of the gate. We were not particularly bothered of what was happening at the side of the drain. So let's shift our focus to wherever we stopped in the previous lecture. And what was the problem that we were trying to address? The problem that we were trying to address was the fact that if we want to apply our signal like this, then the problem that we encounter is we encounter a floating battery. Then we saw that a sufficiently large capacitor acts as a floating battery. But if we have unlike a battery, a sufficiently large uncharged capacitor, right, will not be able to do the job, because ultimately what is a battery? A battery is a storehouse of sufficient amount of charge. And if you have a battery with sufficient charge, then you have a voltage across it. But if you have a capacitor with no charge, right, you don't have any voltage across it. So in order to, it's not only sufficient to use just a large capacitor, you'll also have to charge it with a voltage. And then we said that is then in order to charge it with a voltage, why don't we put a battery of VGQ, right? Why don't we put a battery of VGQ here? So it seems like I'll be able to charge these two plates of the capacitor with the voltage VGQ in the absence of the incremental input. But then we saw that what is the problem? If we do this, the gate of the transistor always remains fixed at VGQ. So that's of no use, because ultimately we want the input signal to appear at the gate of the transistor, right? We want the Y11, incremental Y11 looking into the network to be 0. In this case, Y11 is infinity, because looking into the network, I have a battery. A battery incrementally is a short circuit, right? So this is of no use. So the problem number one here is you have a fixed battery, right? And there is another problem. Problem number two is something that we briefly alluded to in the previous lecture, was that generally in an integrated circuit, or generally in any circuit, you will see that we are given one master voltage source and one master battery, right? One master power supply, from which we need to derive all the other all other voltages that are necessary, right? So I mean, right away here we see that we are using two sources. One is VGQ, one is VDD, which is something that we don't have a luxury of, simply because, I mean, this is a circuit with one transistor. If you have like hundreds of transistors, would you use hundreds of voltage sources? Obviously not, right? So the two problems. The problem number one is gate is held constant, right? So this is problems. And number two is need multiple batteries, right? So let's address the second problem first. Let's say we want to get rid of multiple batteries. We want to generate the voltage VGQ from VDD, assuming VDD is the highest power supply, and that we saw, right? I mean, the requirement of VGQ was far lesser than the requirement of VDD when we took the examples a few lectures back, right? So how can I get if VGQ is less than VDD, how can I get a value, how can I get a reduced value of VGQ from VDD? What is the simplest way? Let's say VDD is 30 volts that we had gotten a few lectures back, and let's say VGQ is supposed to be 3 volts. So what do? You would simply say that if this is VDD, we will put a resistor divider. Let's call this R1, let's call this R2, and if I choose R1 and R2 in such a way that this voltage, what is this voltage? This voltage is R2 by R1 plus R2 times VDD. If I choose this to be equal to VGQ, right, then it seems like I can use this voltage, right? So let me mark this as VG. Then I can look. It looks like I'll be able to use this contraption to bias the transistor, right? Okay, so let's try that. Let's try that and see whether this indeed solves the problem. So what will you do? I will redraw it in such a way that I can get away by drawing only one VDD. So let me call this RL, right? And let's assume we have a battery here of value VDD. Okay. Here I have this capacitor. Here I have my voltage source Vi. And here, instead of that battery VGQ, what we are trying to do? We are trying to replace the battery with a resistor divider R1 and R2, and this is VG. What do you think the value of VG will be? The value of VG in this case will be whatever we saw in the previous slide, right? So VG will be VDD times R2 by R1 plus R2, right? Okay, so now if I ask you a question, can I always replace a battery of a lower value than VDD with a resistor divider like this? Obviously, you can think of multiple cases where we cannot. I mean, one example that we saw was in the introductory lectures, probably in lecture 2 or something, where we saw that if we load a resistor divider with another resistances so that it draws current out of the resistor divider, then the value of the voltage at the resistor divider node will drop, right? So which essentially means that you cannot use a resistor divider always to replace a battery, because a battery is supposed to hold the voltage, right? But how come we are able to use it in this case? We are able to use it in this case because there is no DC current that is getting drawn from this resistor divider, right? What is the DC current that is getting drawn on the left hand side? On the left hand side, what do I see? On the left hand side, I see a capacitor. What is the impedance of the capacitor at DC? It says an infinite impedance, right? What is the DC current that is getting drawn towards the right? What do I see at the right? At the right, I see the gate of a MOSFET, which in essence is again a capacitor. So what is the impedance that I am seeing? I am seeing infinite impedance, which means this I am not drawing any current out of this resistor divider. Since I am not drawing any current from the resistor divider, it really doesn't matter, right? I can essentially replace the battery using the resistor divider ladder. Note that we are not drawing any DC current, right? This is an important distinction to make, right? Since no DC current is being drawn by the resistor divider, right? We can replace the battery Vg cube with the R1 R2 ladder, right? If I had a scenario, let's say instead of a MOSFET, I had another device which draws current, right, into its whatever is equivalent to the gate, then this would have been a problem. We would have had to see what values of R1 and R2 would satisfy our constraint of keeping that voltage at the node Vg constant, right? So, but fortunately MOSFET doesn't draw any current, so we are good. Okay, fine. So this is this essentially solves one part of the problem, right? This solves this problem. We don't need multiple batteries, so this part is solved. What about the first part? What about the signal part of the problem, right? So is the gate held constant? What do you think is going to happen? So let's look at it again from the signal point of view. So let me just sketch the gate side of it. I will not sketch the full MOSFET just for brevity. Let's say this is Vi. You have this capacitor. This is R1, this is R2, and you have the MOSFET here, and so on, and stuffs there. I am interested in the voltage Vg, or let me say I am interested in the total voltage Vg, right? Let me just mark the node Vg here, and then we will see. Okay. So this C tends to infinity. That is something that we have assumed. Okay. So what do you think will this voltage Vg be? I can as well say that I'll do an incremental analysis, right? I can do an incremental analysis just like we did in case of small signal analysis earlier, right? Ultimately, we are interested in the increment in the voltage Vg when I applied a input Vi, right? So what will be the incremental equivalent of this, assuming C tends to infinity and Vi is not at zero frequency, right? So Vi is at omega naught. Let's say Vi is at omega naught, where omega naught is not equal to 0. Okay, because if Vi is at 0, then anyway, no signal, no DC signal will flow from Vi to Vg. Okay, so what will be the incremental equivalent of this? The incremental equivalent of this will be, what should I do? I should replace all the independent voltage sources with a short circuit. So this becomes a short circuit. This R1 remains R1, R2 remains R2. What happens to C? What is C? Infinite capacitor is like a battery. If the infinite capacitor is like a battery, and what do we do with the battery? We short it, so that goes off, right? And what do I have here? I have Vi. So what is the incremental voltage here? Right? It's like, what am I asking, right? It's a short between Vi and that point, so the incremental voltage at this point will also be equal to Vi. So what will be the total voltage at Vg? What will be the total voltage at Vg? The total voltage will be incremental plus quiescent. So incremental is Vi and quiescent is VDD R2 by R1 plus R2. Okay, fine, right? So it seems like this is what we exactly want, right? Seems like this is what we exactly want, at least at the input side, and seems like putting this contraption of a capacitor and this resistor divider ladder of R1 and R2 seems to have done the trick, right? Okay, but not so fast, because you might have already noticed that I have made slight change as to how I have represented the source Vi. I have not marked the source impedance or the source resistance Rs, which I had initially marked at the beginning of the lecture, right? So let's put back the resistance, and let's put back the resistance and see whether it has any effect or not, right? So let's put it back. So what I meant is, let's say you have Vi, the source is always accompanied with some resistance Rs. You cannot wish it away. You have a capacitance C, and VDD, this is R1, this is R2, this goes here, and you have this MOSFET and everything. We are interested on the gate. We are interested in the gate voltage, right? Assuming C tends to infinity again. So what will be the incremental voltage at the gate? The incremental voltage, what will be the incremental circuit? Same old. I will retain whatever, I will retain Rs. Obviously Vi is required because Vi is the incremental source. C, infinite capacitance, acts like a battery, so I can short it, right? R2 goes to ground here, R1 also goes to ground here, right? Because VDD is constant voltage. Then you have the MOSFET, right? Then you have the MOSFET, and let's not bother about the MOSFET right now because we are concentrating on the gate voltage. Okay. So now, what will be this incremental voltage Vg? So Vg, note that Vg will not be equal to Vi, right? Because of what? Because essentially, if I redraw this circuit, what am I seeing? I am seeing this Vi, then you have Rs, then you have a parallel combination of R1 and R2, right? You have a parallel combination of R1 and R2, and this node voltage here is essentially Vg. So what is Vg? Vg is Vi times R1 parallel R2 by Rs plus R1 parallel R2. Okay, fine. So in order to now can you comment on how do you choose R1 and R2 if I want Vg to be almost equal to Vi? Because Vg to be almost equal to Vi is the goal, isn't it? If Vg is almost equal to Vi, then I know that almost the entirety of the input signal appears at the gate of the transistor. So in other words, I do not want any loading. I do not want. So this, what is this stuff doing? This stuff is loading Vi. Correct? Since this is loading Vi, it is drawing current out. Since it is drawing current out, the voltage at Vg is dropping, right? It's not equal to Vi anymore. So you cannot, you don't have any control on Vi, you don't have any control on Rs. However, you have a control on R1 and R2 because you are the designer. You are in charge of choosing the values of R1 and R2, which essentially means that in order to ensure to ensure Vg is almost equal to Vi or IE, to prevent loading, what do we need to do? We need to choose R1 parallel R2 such that R1 parallel R2 is much greater than Rs, right? Mathematically also this turns out to be true. If you see R1 parallel R2 is much greater than Rs, then Vg is almost equal to Vi. And from the assignments in week 1 that we did, you would appreciate that in order to prevent loading, what should we need to do? The part of the network that is loading the actual network should be, the resistance of that should be much higher than the Thevenin resistance of the network that I am looking in. In this case, the Thevenin resistance that we are looking in, this side is Rs, right? And the loading part is R1 parallel R2. So in essentially, if you don't want to load, you have to ensure R1 parallel R2 is much greater than Rs. Okay, fine. So if this is in designer's control, then we are good to go, right? But there is one pesky problem. What is that problem? From where do I get an infinite capacitor, right? So we have been liberally using this assumption that this capacitor that we have here is of infinite value, right? But in reality, nothing is infinite. So we'll have to replace it with a finite value of a capacitor. Now what will happen if I replace it with a finite value of capacitor? What do you think is going to happen? So clearly, if I use a finite value of capacitor and Vi is again at omega naught, not at zero frequency, then there will be some voltage drop across the capacitor, right? So let me still restrict myself to incremental equivalence, and let me just simply say that this is R1 parallel R2 instead of drawing the entire stuff, right? So how would you go about figuring out what is the what value of capacitance that we need to use? One way to think about it is that the value of the capacitance should be such that the voltage drop across the capacitance should be much lesser than the voltage drop anywhere else in the loop, right? So note that this is a loop. This is a loop. If the capacitor would have been of infinite value, what would have been the incremental voltage drop across the capacitor? Note that I am again asking about the incremental voltage drop, not the absolute voltage drop, right? The absolute voltage drop, the capacitor was holding a DC voltage to begin with, that it will still hold, right? But I am not talking about that. I am talking about the incremental voltage drop. If the capacitor would have been infinity, right, the voltage drop across the capacitor would have been 0, right? But in principle, we cannot get any infinite value of capacitance, which means we cannot get any 0 voltage drop across the capacitance. So what is the alternative? The alternative is to say that we need to size the capacitor in such a way that the voltage drop across the capacitor is much less than anything that is anything in the loop in which the capacitor is a part of, right? Now what is a generic way of looking into it? Instead of saying that, I can have multiple loops, this is a particular scenario, I can have multiple loops in the network, you cannot probably identify the capacitor to be a part of one loop, right? It's quite possible. This is a particular case where I can identify a particular loop. But in general, if you face this type of problems of trying to figure out how large a capacitor is supposed to be, or maybe how small a capacitor is supposed to be, right, for in order to pass a signal without causing any voltage drop, or rather without causing any significant voltage drop across it, what would you do? You would try to see what is the Thevenin equivalent resistance that the capacitor sees, right? So in other words, what we are saying is, if I let me mark the capacitor with a different color. In other words, what we are saying is, if I am looking if I am looking at the network sitting on the capacitor, right, what will I see? I will see, in this case, I will see a resistive loop, right? So I can as well, in order to figure out what is the voltage across the capacitor, what do you need to do? I will Thevenize the circuit and assume capacitor to be the load, right? If capacitor is the load, say capacitor is the load, and I am trying to Thevenize the circuit, right? So I am trying to make the equivalent, these two equivalent as far as the voltage drops across the capacitor is concerned, right? I'm trying to figure out what will be this VC, right? What will be this VC? Okay. So then, what should I do? I'm trying to figure out what will be the Thevenin equivalent of this. So in other words, I'm trying to figure out what will be VTH, what will be RTH, right? If I know this, then I can simply say that this is a first order RC circuit, right? And all I need to do is to analyze a first order RC circuit, right? So I mean, you might turn around and tell me that why am I spending so much time on this, because it looks like it's pretty evident looking in the network on the left. What I'm trying to get at here is that it might not be as this evident always. Your network might have lots of other elements wrapped around the capacitor. So then what do you do, right? So use this, please use this as an example of how to go about figuring these things out. Okay, so let's do it with this simple network. So what will be VTH? Your VTH will be what? How will you figure what VTH will be? You open the uh, you open the load, right, and see what will be the voltage that you are supposed to get. What is the VTH? VTH is nothing but, if you open the capacitor, the voltage across the capacitor in the circuit on the left will be nothing but VI, right? Because no current will be able to flow. What will be RTH? Again, let's open the capacitor. What will you do to find RTH? You short the voltage source. You de-energize any source. In case of voltage source, you short it, right? And you see what is the effective resistance. In this case, if you short your voltage source, right? You short your voltage source, then what is the effective resistance? The effective resistance is nothing but Rs plus R1 parallel R2, right? So RTH is Rs plus R1 parallel R2. Okay. So what do you think your VC is? VC is equal to VTH times 1 by j omega c divided by RTH plus 1 by j omega c, right? which I can simplify as VTH by 1 plus j omega RTH, right? Okay. So which I can say that mod of VC, right? Or let me not say mod of VC, let me just keep VC as is. I should also say this VC of j omega, this is not VC of t, right? VC of j omega, VC of j omega will be equal to a magnitude and a phasor, right? So what is the magnitude part of it? The magnitude part of it will be VTH by root 1 plus omega squared, I forgot a c here, omega squared RTH squared c squared, right? I should not say omega because I think I said omega naught there, so this should be omega naught, because I have applied a sinusoid of frequency omega naught, right? And it will also have a phase. What will be the phase? Phase will be minus of tan inverse omega RTH. Okay, so let's not bother about the phase for the time being. All we need to ensure is that if your VC, right, the voltage across the capacitor is what? It should be as low as possible, right? We want the capacitor to be almost like a short, which means what? Which means we want for C to act like a short circuit. We want VC to be equal to 0, or VC should tend to 0, i.e. the denominator should tend to infinity, right, or tend to be as high as possible, right, which means you need to ensure omega naught RTH C should be much greater than 1, which means C should be much greater than omega naught RTH. Okay, so why do we go through all this song and dance? We are doing this all this song and dance just because in principle we cannot get infinite capacitor, which means we need a large capacitor. If we need a large capacitor, we need to figure out what is large, right? Is 1 picofarad large? Is 1 nanofarad large? Is 1 microfarad large? The answer to that is it depends. What does it depend on? It depends on RTH, right? That is good because RTH is in your control. What is RTH? RTH is R1 parallel R2 plus RS. RTH is R1 parallel R2 plus RS. RS is not in your control, but you can increase the value of RTH by increasing R1 parallel R2. That is one good thing. And also, I mean, omega naught might not be in your control, but if you are designing a circuit for high frequency, let's say if omega naught is large enough, then probably you can get away with a smaller value of capacitance. If omega naught is small, then I mean nothing doing. You can either try to make RTH very high in order to keep the value of the capacitance in check, or you just have to go with larger value of C. Okay. Now note that this is the same thing. I mean, we could have come up with the same conclusion without doing all this detailed analysis, right? What is another way of coming at it? I'm sure you know this already, but let me just phrase it for completion purposes. So, what is this circuit? This circuit, when we sketch this circuit, what is the order of this circuit? Note that the order of the circuit is 1. What will you do in order to figure out the order of the circuit? in order to figure out order of a circuit is independent of a source, right? So you short the source. In this case, again, it's a voltage source, so I'm shorting it. Had it been a current source, I would have opened it. So you short the source, and then try to see how many. First, I mean, you can obviously see, in this case, you can see that you have one capacitor and a series connection of RS and R1 parallel R2. So this is a first order circuit. So in general, the trick is to see how many independent initial conditions you can establish in a circuit that has memory elements. Like capacitor is a memory element. If you had inductor would have been a memory element. But the trick is to essentially see how many firstly, how many memory elements you have, and even more important than that, how many independent initial conditions that you can establish in the network. In this case, obviously, I can establish only one independent initial condition, that is the voltage across the capacitor, right? So the order of the circuit is 1. So in a first order circuit, what is the most relevant parameter for a first order circuit? It's a time constant, right? So what is the time constant of this network? The time constant tau is Rs plus R1 parallel R2 times C, right? So it's no doubt that time constant is nothing but RTH, Thevenin equivalent resistance times capacitance. And what is the condition that we are looking for? The condition that we are looking for is the impedance offered by the capacitance. What is the impedance offered by the capacitance? The impedance offered by the capacitance is 1 by mod of the impedance offered by the capacitance is 1 by omega naught C, right? So the voltage drop, if you want the voltage drop across the capacitance to be much lesser than anything that is present in the loop, in a Thevenin loop, right? So what is the trick then? All you have to ensure is that the impedance of the capacitor, right, is much less than the Thevenin resistance, right? So essentially, you have to ensure let me write it in a new page. To ensure negligible voltage drop across a capacitor, we need to ensure the impedance of the capacitor at whatever frequency omega naught, right? So in other words, in this case, 1 over omega naught C, which is the impedance of the capacitor, is much lesser than the Thevenin equivalent, right? The Thevenin resistance of the loop, right? Which essentially means that the constraint directly comes out. The constraint is C should be much greater than 1 by omega naught. So this comes out of plain argument, right? Or in other words, I can also say that this also implies that the time constant of the loop, that is C times RTH, should be much greater than 1 by omega naught. So you can approach this problem from multiple dimensions. You can approach it from the perspective of finding out the time constant and then relating it to 1 over omega naught. You can approach it from the perspective of sketching out a Thevenin equivalent and then finding out the actual drop across the capacitor and trying to minimize it. You can also say that once I have the time constant, right, once I have the Thevenin equivalent resistance, then I don't even have to do anything. I'll just set C to be much greater than 1 over omega naught RTH, and I'm good. Okay. I'll see you in the next lecture.